Hello students, welcome to Kinetic Theory of Gases class. Right, so we'll just have a quick outline what we are going to discuss in this particular chapter, right? And then we'll just go briefly which is required for CET, NEET and JEE. Sorry. Right, we did not go into in-depth of few derivations which are not necessary for any of the competitive examinations. Right, so the quick outline about this chapter is we are going to learn about concept of perfect or ideal gas. That is the first concept that we are going to learn. What is the concept of pressure, different speeds of gas molecules, gas laws from kinetic theory, like we have learned Boyle's law, Charles law and Avogadro's law in as a independently, but we are going to look into it or look at those gas laws in relationship with kinetic theory of gases. Degrees of freedom, law of equipartition of energy, total internal energy of a gas and molar specific heats of a gas, right? So starting with the first concept, that is concept of a perfect or an ideal gas. Obviously we are in a real world, so we will not see that every gas that we see behaves ideally, but first we have to set a benchmark. What is an ideal gas, isn't it? Right? Or we have to at least have a comparison. When can I say that a gas is an ideal gas, or when can I say that a real gas is an ideal gas? Right, so that comparison is over here. What is that? Any gas which obeys Boyle's law, Charles law and pressure law can be called as an ideal gas, right? Like that, from this we can say that all the real gases, they don't obey these laws very strictly. At some point there will be some variation of these gases from these laws, right? So first let's see what is Boyle's law. Boyle's law is PV equals to constant at constant temperature, and Charles law states when pressure is constant, volume is directly proportional to temperature, right? And what is pressure law? Under constant volume, pressure is directly proportional to temperature. Any gas which always follows these three laws can be called as an ideal gas. But we are going to learn some more criteria about ideal gas, or in-depth criteria in some time. If you want to plot a graph between pressure, volume, number of moles, temperature and pressure, what is the ideal gas equation? PV equals to mu polarity, pressure, volume, number of moles, gas constant, temperature, right? If you look at PV by mu T, this is gas constant, right? Against gas constant should be always constant. It should not vary with respect to pressure or temperature. But if you look at the graph over here, the dotted line represents how the y-axis is changing with respect to pressure for an ideal gas. You can see that in case of an ideal gas is constant. R is constant for an ideal gas. But what happens in case of real gases? We are seeing these real gases at different temperatures T1, T2 and T3. And you can see that a real gas will deviate from the ideal gas equation slightly, and then it overshoots up. Similarly, for different temperatures you have different curves like this. If you look at the comparison of temperatures, you can see that temperature T1 greater than T2 greater than T3. This is from the experimental result. From this particular graph, what can you infer about real gas and ideal gas? Can I, or let me ask you a question. When can I say that a real gas is behaving similar to an ideal gas? At two particular locations this is happening. One is over here, right? And one is over here. But tell me, how can I put it in particular? How can I put it in a proper statement? Let's talk about temperature. When temperature is very high, can I say that a real gas is behaving like an ideal gas, right? So I can say if temperature is high, real gas behaves like an ideal gas. Now, what about pressure? Let's look at it on the x-axis. When pressure is very small, that is right over here, you can see that the real gases and ideal gases are behaving the same. So I can also say that if pressure is, sorry, let's erase this part. If pressure is very less, then also I can say that real gas behaves just like an ideal gas, isn't it? So from this, what can we say? Under low pressure and high temperature, a real gas can behave as an ideal gas. You may ask, at higher temperatures also this is happening because of the right side part of the graph, because of this. But higher temperatures also mean over here, over here, over here as well. As you are going to much higher temperature, it is again deviating from the ideal gas curve, isn't it? So you cannot just define for a higher pressure. But when I say zero pressure, it means there is only one single point where there is zero pressure, isn't it? So that's why at lower pressures and very high temperatures, a real gas can behave as an ideal gas, right? Pressure is equal to P naught into 1 plus alpha P delta T. Similarly, volume is V naught into 1 plus alpha V delta T. Alright, this is called as coefficient of pressure and coefficient of volume. These two should be almost similar. Why they have to be almost similar? Why? Because P dash V dash by T2 is equal to P naught V naught by T1, isn't it? So as long as this is being satisfied, this alpha P and alpha V should be also same. Right, that is the condition for an ideal gas equation, isn't it? That's why pressure coefficient and volume coefficient are almost same. The third point is molecules are infinitesimally small. What is this infinitesimal? You might have learned this in many scenarios. Infinitesimal means extremely small. You cannot define how small they are, right? They are extremely small atoms. And the fourth point is there should not be any force of attraction between its molecules. See, by just telling you the main point, you can infer different things from this. Like for example, if I tell you that there is no force of attraction between its molecules, it implies I should never be able to convert these gases into liquid form, isn't it? Why? If I convert it into liquid form, in liquid, the force of attraction between the molecules is greater than that of the gases, isn't it? So think which gases are very difficult to convert them to liquid form in reality. We have hydrogen, we have oxygen, right? These two gases are extremely difficult to convert them to liquefy them, isn't it? And basically most of the inert gases are also same, isn't it? So most of the inert gases, hydrogen and oxygen, these you can call them as gases which behave close to ideal gas, but they are not perfect ideal gas. Obviously none of the real gases are perfect ideal gases. It's a hypothetical situation where you have to understand that under certain conditions real gases can behave like ideal gases. Okay, now every ideal gas should or will be able to follow one particular equation called as an ideal gas equation, which is given by PV equals to nRT, where P represents pressure, V represents volume, N represents number of moles, R represents gas constant and its value is 8.314. T represents absolute temperature. That means basically Kelvin, right? Now in this we are going to discuss mostly about this N and R. How can we convert this into a different constant called as a Boltzmann constant? Okay, let's take number of moles into R. This number of moles can be written as what? Number of moles can be written as total number of molecules N divided by Avogadro number into R, right? This particular value, that is gas constant by Avogadro number, can be represented with a new constant called as Boltzmann constant, that is N into K. So the relation between R and K is what? R is equal to sorry R by Na is equal to K, or R equals to K times of Na, right? Na is the Avogadro number, and value of Avogadro number is how much? Na is 6.023 into 10 power 23 items or units. K is called as the Boltzmann constant. Alright, remember every ideal gas should follow this ideal gas equation. Doesn't matter how many moles or what is the volume, what is temperature, it doesn't matter. Any gas should follow this. It doesn't even bother with what kind of process it is following. That is whether the gas is following constant pressure, constant volume or constant temperature. Concept of pressure of the gas. We all see that, or we all realize that gases exert pressure, but we should know why they exert pressure. What's the reason? Like for example, we start filling air into a balloon, right? You can see that there is some pressure exerted by the gas inside the balloon. That's why you see the elongation or expansion of the balloon against the elastic force of the balloon. But why it has to expand, or why there is some pressure? Because of the gas. They are just small molecules, isn't it? To understand this particular concept, we have to, or we are going to link it with Newton's laws of motion. First, in Newton's laws of motion, we have learned one important concept. What is that? That is, a rate of change of momentum of a particle or a mass is nothing but the force. Right? The net force applied on it is what? dp by dt. Right? Momentum is what? M into V. Right? D by dt of m into V is m into dV by dt, which is m into A. This is the force. Right? So what actually happens is, for any gas, the molecules of the gas are moving with some speed. Based on the temperature, the different molecules will have different speeds, right? But on an average, most of the gas molecules will have the same speed, right? Now, if you confine these gas molecules within a particular container, let's take a cubical box like this. You have confined all the gas molecules within this container. Okay, so when there is random motion of these gas molecules, they will obviously collide with the walls of the container, right? And every molecule has some mass. Let's say it is moving with some speed v. After collision, let's say it is coming back with the same speed v. Then what is the change in momentum for this particular gas molecule? it is 2 mv, right? And let's say the collision time is delta t. So within this delta t time, it's the momentum of the molecule changed this much 2 mv. So obviously this becomes what? Force. So F is equal to 2 mv by delta t. But don't you think that all these gas molecules will not collide at only one single point in the entire wall, isn't it? Basically, based on symmetry and common sense, we can say that all these gas molecules, they collide with the walls uniformly at all the locations of the wall. Let's say the area of this wall is A, then force by area, which is 2 mv by A times of delta T. This becomes what? Pressure. This is how the pressure arises due to a gas, right? Now we will see some of the postulates of kinetic theory. That is, in order to see whatever the concepts that we are going to learn in this particular chapter, in order to go ahead with them, we need to assume few things for an ideal gas. And remember, these are true only for an ideal gas. These are not true for any gas. Okay, coming to the first postulate or the first assumption that we are going to say is all the gas molecules are rigid, right? Rigid, very small in size and identical. And the volume of the gas molecules is negligible compared to the volume occupied by the gas. These are basically true, but we are just assumption. We are doing an assumption of these things initially before we derive anything related to kinetic theory. Okay. The second point: no force of attraction between the molecules. Very important. There is no force of attraction between the molecules. But what happens when two gas molecules come very close to each other? Then you can say that there is some kind of repulsive force between the two gas molecules. Even though there is no physical contact between them, you can say that a collision had happened, right? So that particular event where two gas molecules come very close to each other in such a way that after coming close to each other, they change their or they deviate from their original path or original trajectory. You can say that an event of collision had happened, right? So under this, you can write collision when two gas molecules come very close, they experience a repulsive force between them, right? Now, the distance traveled by a gas molecule between two successive collisions, right, is called as mean free path. We are going to, learn one particular formula related to mean free path at the end of the chapter. So just try to keep up with the terminology in this case. What does that mean free path is? distance traveled by gas molecules between two successive collisions. Okay. The next postulate is the collisions between gas molecules and the walls of container are elastic in nature. Elastic in nature means no loss of kinetic energy, isn't it? That is how elastic collisions happen, right? Momentum is conserved along with kinetic energy is also conserved. The next postulate is the time of collision is very small compared to the time taken between two successive collisions. Okay, these are the important postulates that we have to keep in mind before we try to derive anything related to kinetic theory. All right. The next concept we have is formula for the pressure of an ideal gas. We all have learned the important formulas for the velocities. We haven't learned yet, but we know that we are going to learn about RMS speed, average speed, most probable speed in some time. But the basics of that particular formulas will be starting from here. That is the pressure of an ideal gas. We are going to derive when you put an ideal gas in a container, a cubical container like this. We know that it exerts some pressure. We are going to find out what is this pressure based on simple mathematical concepts and little bit of physics, nothing else. Okay, so let's start with the basic terminology, what we are going to define for this to derive this. Okay, let's first one is with the length of this cube is L. It's a cube, right? And it is placed along X, Y and Z axis, right? M is mass of each molecule of a gas. N is number of molecules present in the gas, right? V bar is velocity vector of the gas. Since it is having velocity, since it's a velocity vector, I can write V bar equals to Vx I cap plus Vy j cap plus Vz k cap. Remember, every gas molecule will move in random directions. On an average, remember whatever the velocity we are writing here, this is on an average, right? V bar is Vx I cap plus Vy j cap plus Vz k cap. Don't you think that these velocity components along x, y and z axis should be the same? That is Vx equals to Vy equals to Vz, right? Vx equals to Vy equals to Vz. Okay, these are the initial parameters that we are going to define. If at all we come across new parameters, we'll define them at a later stage. All right. So getting ahead to find the formula for pressure of an ideal gas. First, let's take a molecule of the gas having a mass m, right? And it is having a velocity v like this on the x direction, isn't it? Right. So what is its initial momentum? Initial momentum is mv. After collision, it will come back with the same velocity v. So final momentum is again mv but with a negative sign. Why? The direction of velocity had changed, isn't it? So what is the total change in momentum? It is 2 into m into v. Alright. Now, how much time it takes for this gas molecule to come back to this wall again? To come back to this one. Can I say it takes 2L by V time, because it has to go back to the other wall. do a collision with the other one, and come back to this one. Total distance traveled is 2L and it is moving with a speed v. So time taken is 2L by v, isn't it? Now I know that this much momentum has changed in this much time for the gas. So what is the force exerted by this one molecule of the gas on the wall? It is 2mv by 2L by v, right? This is for just one collision, but how many collisions will happen in 1 second? In 1 second, Vx by 2L collisions will be happening, right? Right, in 1 second, Vx by 2L collisions will be happening. So the total force is equal to 2mvx into Vx by 2L. Since we are dealing with only x-axis, I have changed the velocity to be Vx, which would make it as mvx square by L. This is the total force, right? But I don't have just one molecule, right? I have n molecules, right? And let's assume all these n molecules have different velocities in the x direction. So the total force created by all these n molecules, total force for n molecules, can I say it's nothing but the individual sum of the forces, which is m times of Vx1 square by L plus m times of Vx2 square by L, so on to m times of Vxn square by L. Right here I can take m by L constant, it is Vx1 square, Vx2 square, so on to Vxn square. Right, we have to do a little bit of manipulation over here that we will do now. Remember, this is the total force by all the n molecules acting along the x direction. Now the pressure is what? Force by area, which is force by L square, which would make it as m by L cube into Vx1 square plus Vx2 square plus so on to Vxn square. Let's multiply and divide with n. What does this term shows us? What does this term tells us? It is sum of squares of individual velocities whole divided by the total number of terms, isn't it? Right? So what do we call this? What do we call this as? It's basically RMS, but it's square of RMS, isn't it? So this can be written as mn by r cube, mn by L cube into VRMS square, but only in x direction, isn't it? If you look at that earlier vector form, we wrote v bar equals to vx I cap plus vy j cap plus vz k cap. If you take the magnitude, v bar square is vx square plus vy square plus vz square. We also know that vx equals to vy equals to vz, right? So this can be written as 3 times of vx square, 3 times of vy square, 3 times of vz square. This RMS is along the x direction, which can also be represented as mn by L cube into v bar square by 3 using the first equation, isn't it? Which would make it as 1 by 3 mn by v times of v bar square. Sorry, v bar square it is. Why v? L cube is nothing but the volume of the cube, so I represented it with v. Now let's see this, what is there in the square bracket. Small m is the mass of each molecule. Small n is the total number of molecules. So mass of each molecule into total number of molecules can be called as the total mass of the gas. divided by volume. Mass by volume is what it is. So we have pressure equals to 1 by 3 into rho into Vrms square. This is how we have derived the formula for pressure in terms of density and Vrms. So from here, let's try to write down the formula for Vrms. Vrms can be written as 3p by rho under root. Isn't it? I just shifted this 3 rho to the other side and also the square. We can also find a relation between pressure and energy this way. Pressure is equal to 1 by 3 rho Vrms square, or it can also be written as 2 by 3 into half rho Vrms square. What does this look like? Half rho V square. Don't you think? Okay, what is density? Density is mass by volume. So half into mass into velocity square. Can I call it as translational kinetic energy? Because translational kinetic energy is half mv square. If I divide this kinetic energy with volume, can I call it as kinetic energy per unit volume, which we will represent it with E, which is 2 by 3 E, 2 by 3 times of, where E is called as what? Translational kinetic energy per unit volume, and it is given by half rho Vrms square. This is the relation between pressure and translational kinetic energy per unit volume. Please be very careful with E. It's not the total energy. It is the translational kinetic energy per unit volume. This is how we have derived the formula for pressure and its relationship with velocity as well as density of the gas. Right? The next concept we have is different speeds of gas molecules. Right? So we have three important speeds that we have to learn about. That is, first one is called as average speed. And you know what is average? How to find average? It is summation of individual speeds divided by the total number of speeds. Let's say I have n molecules. All the n molecules might have different instantaneous speeds. At that instant, these are the velocities. Okay. Divided by the total number of molecules will give me the average speed, and it is given by the formula. You don't have to learn the derivations as such because it's out of the syllabus for any of the competitive exams, but you have to remember these formulas, right? What is the formula? It is 8RT by pi m under root. Remember, T represents the absolute temperature, m represents here molecular mass of the gas. Molecular mass. R is the gas constant, right? The next one we have is Vrms. Vrms is what? So, root of mean of the squares. That is, first you square them, take the mean and take the root of it. And it is given by the formula root over 3RT by m. The third kind of speed that we have is V, most probable. Most probable means uh, which gases, or which more number of molecules of the gas have the same or similar speed. That is called as a most probable speed, right? And it is given by the formula root over 2RT by m. Remember, these formulas are important, very important. You just get questions based on these formulas, nothing else. And if you look at all the three formulas, only the initial coefficient is different. That in the V average 8 by pi, Vrms it is 3, V most probable it is 2. Okay, so this is very important. Alright. The next concept that we have is degrees of freedom. What do you understand, or what is the meaning of degree of freedom for a gas molecule? All right. So for that to understand, we'll first go back to kinematics, that is motion in a two-dimensional plane. Okay. So let's say a particle is moving along xy plane. Its velocity is in xy plane. Can you tell me how many components it has along, you know, what are the different components this velocity can have if it is moving only along xy plane? It has x component Vx as well as y component Vy, right? And I can say that this Vx component is independent of what is happening along y direction. Why? Because these two are perpendicular, right? Since I'm talking about a small particle, its size is very small, so you don't expect any rotational motion out of the small particle. But what if I have two particle system like this, right? Now this two particle system can go translationally along x-axis, can go translationally along y-axis, and go translationally along z-axis, right? So all these three translational motions can be distinguished independently, isn't it? We can distinguish whether the particle is going along x-axis, y, or z-axis, right? So it has 3 degrees of translational freedom, or I can say that it's the degrees of freedom related to translational motion are 3 in number, right? So degrees of freedom in translational motion for this are 3. Okay, what about its rotation? I can make this two particle system rotate about this axis and also about an axis which is going into the page, and also about an axis which is passing through both of them, like this, right? So in all the 3 cases I can have rotational kinetic energy, isn't it? Or I can make the two particle system rotate in different you know with the different axes, isn't it? But if you observe carefully, this is fine, these two axes are fine, this one and into the page, but there is a problem with this particular axis. Why? The axis is passing through the two particles, right? Since these are, infinitesimally small particles, the rotational kinetic energy or the moment of inertia of these particles about this axis I1 is very small, isn't it? If moment of inertia is very small, the kinetic energy related to that moment of inertia is also very small. So this particular axis is of no use for us, or I can say that there is no energy associated with that particular axis, but I can have energy in a translational motion along x-axis, y-axis and z-axis, as well as rotational kinetic energy about these two axes. One is into the page and one is passing through the perpendicular bisector, right? So rotationally it has 2 degrees of freedom. Fn rotational is how much? 2 degrees of freedom for a two particle system. So total it has 5 degrees of freedom for a two particle system. So degrees of freedom is nothing but in how many ways a system or a molecule can have different energies. This can be called as a degree of freedom. Okay. In our syllabus, we have to learn about degrees of freedom for only like 3 kinds of molecules. First one is for a monoatomic molecule. So monoatomic gas, there is no molecule if it is monoatom. It's a monoatomic gas. Monoatomic gas means we have just one atom, one tiny atom. So it has 3 degrees of freedom, X, Y, and Z. So its degrees of freedom are 3, and these are translational only in translation. All right. Now the second one is diatomic or linear triatomic. It's not diatomic or linear triatomic. What I mean to say is you'll find same degrees of freedom for a diatomic molecule as well as a linear triatomic molecule. Okay, so how does a diatomic molecule look like? Two atoms separated by a distance, right? Obviously it has, on a translational level, there are 3 degrees of freedom, but on rotational level it has 2. Total we have 5 degrees of freedom. It doesn't matter whether I have 2 molecules, 3 molecules, or 4 molecules as well. The total degrees of freedom in case of a linear molecule, this is like a linear molecule, right, is always 5, out of which 3 are translational, 2 are rotational. Okay. The third molecule that we have is non-linear triatomic molecule. Non-linear triatomic molecule means it basically looks somewhat like this, right? So for any molecule, 3 translational are important. It has 3 translational, that is fine. Let's see about rotational. Okay, it can rotate about this axis, about this axis, and about this axis, right? So it has 3 rotational and 3 translational. Altogether we have 6 degrees of freedom. Why are we learning this? We are learning this because this is the basic requirement to calculate specific heats, and based on the next concept that we are going to discuss called as law of equipartition of energies, we are going to see how different kinds of molecules have different energies associated with them. It is totally based on degrees of freedom. Like I said, if there is a degree of freedom, or if any molecule is having some degree of freedom, it means there is some energy associated in that particular direction, right? Anyway, we'll discuss that in the next concept. The next concept is law of equipartition of energy. First, let's understand what is this law. It's pretty simple, so please try to focus. Law of equipartition of energy states that in classical physics, the energy associated with each molecule of gas is equally divided among all the degrees of freedom under equilibrium temperature. What is the meaning of this? Let's understand this with an example. Let's take a monatomic gas, like argon, right? Let's take or hydrogen. Let's take hydrogen. All right, hydrogen atoms. Okay, so it's a monatomic gas. If for a monatomic gas, it has, degrees of freedom 3. And if I say that the energy associated with each molecule of one hydrogen atom is x joules, this is for just one molecule, then this x joules is equally partitioned into the 3 degrees of freedom. These 3 degrees are translational, right? So x by 3 amount of energy will be along x-axis, x by 3 amount of energy will be along y-axis, x by 3 amount of energy will be along z-axis. This is called as law of equipartition of energy. What does the law say? It is the energy associated with each molecule of gas is equally divided among all the degrees of freedom under equilibrium temperature. Right? If a gas is having 5 degrees of freedom, for the same example, let's take the degrees of freedom are 5. Right? Then if the molecule is having x joules, then the energy associated with each degree of freedom would be x by 5 along x-axis, x by 5 along y-axis, x by 5 along z-axis, and x by 5 along the two rotational axes. Right? This is called as law of equipartition of energy. And how much is this energy equal to? This energy for each degree of freedom is half kT, right? Along each degree of freedom for each molecule. So if a molecule is having f degrees of freedom, can you tell me what will be the total energy? E total is f times of half kT, that is f by 2 kT for one molecule, right? If I have Avogadro number, if I have Avogadro number of molecules, then what will be the total energy? E total becomes Avogadro number into f by 2 kT. N into Avogadro number into k is called as what? Remember, k is the Boltzmann constant. So Avogadro number into k is called as gas constant R. That is f by 2 RT. This is for, I said one. This is for Avogadro number of molecules. One Avogadro number of molecules is nothing but mole, right? For 1 mole of gas. If I have n moles, then what will be the total energy associated? For n moles of gas, the total energy associated is n times of f by 2 RT. This is the energy of any gas, right? So in the last concept, we have discussed about law of equipartition of energy, right? And that energy is arising because of the kinetic energy of individual molecules, right? With respect to temperature. Now, we may call it as kinetic energy of individual molecules, but that represents the internal potential energy of a gas, or you can also call it as internal energy of a gas. So we can define the internal energy of a gas, which is represented with U, is NF by 2. This is for n moles of a gas. For n moles of a gas, the internal energy associated, or the total internal energy, is NFRT by 2. Or change in internal energy delta U can be written as NFR by 2 times of delta T, right? If it is for 1 mole, n becomes 1, it becomes Fr by 2 delta T. This is delta U for 1 mole of a gas, right? The next concept that we have is molar specific heats of gas. We can define, different molar specific heats for a gas based on the process it is undergoing. But it will be too many number to read, but we are going to focus mainly on two important molar specific heats called as Cp and Cv. Cp is called as molar specific heat at constant pressure, and Cv is called as molar specific heat at constant volume, right? So what is the definition of this molar specific heat? We have learned about specific heat, right, in calorimetry and all. What is the meaning of specific heat? It is the amount of heat energy required to raise the temperature of a unit mass of a substance by 1 degree Celsius, right? So if I talk about molar specific heat, can I say it like this? It is the amount of heat energy required to raise the temperature of 1 mole of a gas by 1 degree Celsius. I can raise the temperature under different conditions, right? So out of all those conditions, I'm considering one condition, two conditions. One is at constant pressure and one is at constant volume, right? So delta Q is equal to N into Cp into delta T if I am providing heat energy to a gas which is always maintained at constant pressure, right? So for delta Q amount of heat energy I supply, the change in temperature will be delta T. N will be the number of moles, Cp is the molar specific heat, right? Similarly, if I am providing heat energy to a gas keeping volume as constant, then what happens? Delta Q is equal to NCV delta T. Right now we are going to find some interesting facts about these things in some time. What are those? That is how I can represent this Cp and Cv, that is molar specific heats, in terms of degrees of freedom. Alright, to understand that we need to start with the first law of thermodynamics. Okay, we will just borrow that one part from thermodynamics and utilize it over here. Alright, right, so that one part from thermodynamics is delta Q is delta U plus W, where W is nothing but P delta V. Right. So I have delta Q equals to delta U plus P into delta V. We know what is the formula for delta U, we have found out just now, right? So since we are dealing with molar, let's fix that moles to 1 mole. Let the number of moles to be just 1 mole. Okay, so delta Q becomes, what is delta U? It is 1 into Fr delta T by 2 plus P delta V. Now let's analyze this equation under two conditions. The first condition is at constant volume. What happens to this equation at constant volume? Yes, delta V will become 0, right? Delta V is 0. Then what happens to this equation? Delta Q is Fr delta T by 2. But at constant volume, for 1 mole of a gas, what is delta Q? We have done it just now. That is Cv into delta T is equal to Fr delta T by 2. Delta T gets cancelled on either side, so Cv is nothing but Fr by 2. That is, molar specific heat at constant volume is given by F into R by 2. This is fixed for a gas having F degrees of freedom. Right? Is it clear? Next. Now, under second condition, that is at constant pressure, what happens to the gas equation? What happens to the thermodynamic first law of thermodynamics? Delta Q is delta U plus P delta V, or delta Q equals to, what is delta U? It is N Cp delta T plus P delta V, but we have taken 1 mole, so N is 1. Sorry, one mistake here. Delta Q is NCP delta T, delta U is FR delta T by 2 plus P delta V. What happens to P delta V? Let's see. PV equals to nRT. Since the number of moles we have fixed to 1, we'll take it as 1. Under constant pressure, this is constant pressure condition, right? At constant pressure, if I take derivative, P into delta V is R into delta T, right? So this can be replaced with R delta T over here, right? Since the number of moles are 1, this is kept as 1. Delta T can be cancelled on either sides. Cp can be written as F by 2 plus 1 times of R. So I have written the molar specific heats at constant pressure and constant volume in terms of the total degrees of freedom and gas constant R. Right? Now, what will be the ratio of these two terms? What will be the ratio of molar specific heats called as Cp by Cv? We represent it with gamma if you remember this. Right? Cp by Cv is called as molar specific heat ratio and it is given by Cp is F by 2 plus 1 times of R divided by F by 2 times of R. If you simplify it, you will get 1 plus 2 by, right? So let's try to write down the value of gamma for three different kinds of molecules. Gamma for monoatomic gas. Monoatomic gas means degrees of freedom are 3, which would be 1 plus 2 by 3, which is 5 by 3. Gamma for diatomic, degrees of freedom are how much? 5, which is 1 plus 2 by 5, 7 by 5. In case of triatomic, when I say triatomic, it is non-linear. That is understood, obviously. Okay, F is equal to 6. So degrees of freedom would be how much? 1 plus 2 by 6, which is 4 by 3, isn't it? So this is how you calculate gamma based on the degrees of freedom. So apart from this translational and rotational degrees, you have one more degree called as vibrational. We generally don't use that vibrational degree of freedom because that's not really part of your syllabus. Okay, I hope you have understood molar specific heats so far without any confusion.